Okay, I guess we should start. We are very happy to have Shira Zerbib talking to us from Iowa State University, and she's going to talk about dividing cakes with topological Hall. Go
Thank you
ahead.
so much. Thank you again for inviting me to speak in your seminar. I'm very happy to speak here today. And this is a joint work with Ron Aharoni, Berger, Joe Briggs, and Erel Segal-Halevi. So, so the cake part is mainly a motivation to describe two things that I want to focus on today. The first one is a new family, or at least a newly defined family of hypergraphs that I will call fractionally balanced hypergraphs that I want to discuss and investigate their mainly their matching numbers. And the second one is to introduce a topological tool known as the topological Hall theorem that is not new, but not uh, widely used, or at least not enough widely used. So I wanted to show you how nice of a tool is it to investigate hypergraphs. So let us start with the theorem that I mentioned in the pre-seminar. This is the KKM theorem due to Knaster, Kowaltowski, and Mazurkiewicz from 1928. And it tells us that if we have the n-1 dimensional simplex, in this example, the 2-dimensional simplex, and we have n sets, sorry, this should be n sets covering delta n minus 1. And these sets are closed and they have some nice covering conditions. So vertex 1 must be in the set R1, vertex 2 must be in R2, and the face 1, 2 must be in the union of R1 and R2. And similarly, vertex 3 must be in R3, and the face 1, 3 should be in the union of R1 and R3, and so on. If we have this condition that is written as for every phase sigma, the phase sigma is contained in the union of the Ri's, where I is a vertex in sigma, then the conclusion of the theorem is that all the sets R1 to Rn must intersect. So in 1982, Gale proved a colorful version of this theorem. So now instead of having one KKM cover, a KKM cover is a cover as in the KKM theorem. So a cover that satisfies these two conditions. So now instead of one KKM cover, we have n KKM cover of the n-1 dimensional simplex. So for example, here we have 3 KKM covers of delta 2. The red KKM cover, the blue KKM cover, and the green KKM cover. Then Gale tells us that we can find a permutation in Sn such that picking the pi I set from the cover AI and looking at all these n picked set, we get a non-empty intersection. So in this example, we can pick the first set from the green cover, the second set from the red cover, and the third set from the blue cover, and get that these 3 sets intersect. Okay, and this is true anytime we take any n KKM covers of the simplex. And now let us see how this can be connected to cake division. Okay, so in this setting, we have a set of n players, say 3 players here, and the cake, which is a one-dimensional object. So you can think instead of a cake of any one-dimensional object that you want to divide between n people. And each time I introduce a partition of the cake into number of players pieces, so here 3 pieces, each one of the players has a preference of its the favorite piece that he wants. So for example, if I partition the cake like that, then the green player wants the rightmost piece, and the red and blue players want both the middle piece. And if I partition the cake in a different partition, then suddenly red and green want the leftmost piece and the blue player wants the middle piece. Okay, and what I'm looking for is an entry-free division of the cake, namely a partition in which each of the players prefer a different piece. Okay, and let me just mention here that a player can have more than one piece that he prefers best. Okay, so we are asking if and under which conditions there exists an entry-free division of the cake. How does this relate to the theorems that I mentioned before about the simplex? So we can observe that each point in the simplex corresponds to a partition of the cake into n pieces. So each point in the n-1 dimensional simplex gives us a partition into n pieces, where the leftmost piece is of length x1, the second piece is of length x2, and so on, where I'm thinking of the simplex as embedded in Rn in the standard way. So we can use the preferences of the n players to define n covers of the simplex. We do that as follows. So for example, we want to define the red cover. So R1 will be the partition in which the red player prefers piece 1. R2 will be the partitions in which the red player prefers piece 2, and so on. And we do the same for B1, for the blue player and the green player. Okay. So for example, this partition is in R1 because the red player prefers piece 1. It is also in B2 because the blue player prefers piece 2. And it is also in G1 because the green player prefers piece 1. And what we want is exactly the conclusion of the colorful KKM theorem. So we want a piece, we want a partition, namely a point in the simplex, that is in the intersection of sets coming from each one of the n different KKM, n different covers that we get, and corresponding to n different vertices of the simplex, right? Such a partition will correspond to an entry-free division of the cake. Okay. A theorem of Stromquist and Woodell from 1980 tells us that such a partition always exists under 2 conditions. The conditions are that the player are hungry and their preference sets are closed. What we are going to see soon is that these 2 conditions are exactly the conditions of the colorful KKM theorem. So what actually is discovered lately, that the Stromquist-Woodell classic cake division theorem is actually the colorful KKM theorem in disguise. So preference sets are closed, meaning just that these Ri, Bi, Gi are closed. What does it mean that the players are hungry? It means that whenever I introduce a partition, each player wants something to eat. He is hungry, or she is hungry, so they don't want an empty piece. So for example, in the partition corresponding to vertex E1 of the cake, there is only one non-empty piece, right? There is one piece that is entire, x1 corresponds to the entire cake, and there are two empty pieces or pieces of length 0 corresponding to x2 and x3 that are 0. And therefore, since each one of the players are hungry, they will all prefer piece number 1 in this partition. So E1 will be in R1 and will be in B1 and it will be in G1 as is needed in the conditions of the KKM covers. And this will be true for any point in the boundary of the simplex. Okay, so the hungry player condition is exactly the covering condition of the KKM theorem. Okay, so this is the classic EntryFree Division theorem. And what we want to do is now to generalize this theorem to more than one cake. So now instead of having just one-dimensional object that we want to divide between a set of people, we have multiple one-dimensional objects that are to be cut into different number of pieces. And we want to assign to each player a tuple of pieces, one from each cake, such that the assigned tuples are pairwise disjoint because we don't want them to fight over pieces. And the question is again, what conditions allow us to do it? So this motivates what we are doing in this talk. But before we do that, I want to present another proof of the Stromquist-Woodell theorem. So far we saw one proof using the colorful KKM theorem. I want to present another proof because this proof we will be able to generalize in order to discuss multiple cake division. So the proof that I'm going to discuss is more recent. And in order to discuss it, I need some matching theory. So a matching in a hypergraph H is a set of pairwise disjoint edges. And we denote by nu of H the matching number of H, which is the maximum size of a matching. A fractional matching is a fractional generalization of the matching concept. So it's a function from the edge set to non-negative numbers, such that the sum of the weights on every vertex, the sum of the weights of the edges containing any vertex is not more than 1. Okay, so we call this sum the degree of the vertex in the fractional matching F. Okay, and we define this, the size of F to be the sum of all the weights in F. And now the fractional matching number, which we denote by nu star of H, is the maximum over all fractional matching of H of their sizes. So by definition, it is always true that the matching number is less than or equal the fractional matching number. This is just because in the fractional case, we're taking the maximum over a larger set. But Canning tells us that if we are in the special case where H is actually a graph and not only just a graph, but a bipartite graph, then the matching number and the fractional matching number are the same. And we're going to use that. Now, a hypergraph H is called R-partite if we can partition the vertex set of H into R sets such that every edge intersects every side. These sets will be called the sides of H, or the vertex sides. So every edge must intersect every vertex side in exactly one vertex. So this is just a generalization of the notion of bipartite graphs. And now I want to introduce the family of hypergraph that I promised that I'm going to discuss. And these are fractionally balanced hypergraphs. So an r-partite hypergraph is called fractionally balanced if there exists a fractional matching f of this hypergraph and constants C1 to CR, such that if I take a vertex in VI and look at its degree, the sum of the weights of the edges containing V, then this degree is CI. So on every side, the degrees are constant. Okay, so in V1, all the degrees are C1. In V2, all the degrees are C2, and so on. So here are two examples. Say we take the complete bipartite graph on M and N vertices. Then I claim that this is a fractionally balanced hypergraph, or graph in this case. Why? First, it is bipartite, so the first condition holds. And second, I can find a fractional matching such that the degree is constant on each one of the sides. If I take the weight of every edge to be 1 over the maximum between M and N, then on the first side, I get N over max Mn to be C1. And on the second side, I get M over max Mn to be the constant C2. Okay? Any questions so far? Okay, here is a negative example, a hypergraph that is not fractionally balanced. So this hypergraph is still bipartite, but I claim that there is no such fractional matching that is constant on every side. Why is that? So we have to give some weight to this edge. Say I give it weight 1, it doesn't matter. And then I have to give some weight to these two edges, say A and B. Now I want A plus B to be 1 on this vertex because the degree of this vertex is 1, right? The sum of the weights of the edges containing this vertex is 1. So I need A plus B to be 1. But then one of them must be less than 1, which is not the degree of this vertex, which is 1. So the degree of one of these vertices will not be 1. So it won't be the same as the degree of this vertex. Okay, so this is not fractionally balanced, but this one is. Okay, questions? Good. So one observation that we are going to use is that if H is fractionally balanced, then the fractional matching number of H is the minimum of the size of the vertex sides. So, for example, here, one of these will be M. Say if M is less than or equal N, then the size of this fractional matching is M, which is exactly this observation. Okay, so now we are ready to see another proof of the Strong-Quist-Woodall theorem, and this is due to Monnier and Su from 2018. So we take Q to be the set of players. So we have player U1, U2, UN. Remember, we have N players. And for every partition P of the cake, we define a bipartite graph G of P in the following way. So the sides of GP will be this set of players U and the set of pieces 1 to n. And the edge set will be all the pairs Uij for which player Ui prefers piece J given the partition P. Okay, so I match player to pieces they prefer in the given partition P. And what Monnier and Su proved is that there exists a partition so that GP, there exists a partition P for which the corresponding bipartite graph G of P is fractionally balanced. And now we see why fractionally balanced are important for cake division. So by this theorem and by the observation we had before, for this partition P, the fractional matching number of G of P is n, because remember by the observation, the fractional matching number is the minimum side size, and here two sides are of size n, so the fractional matching number is of size n. But by Kenning's theorem, this means that the matching number of G of P is of size n. So we have a matching of size n. G of P has a matching of size n. U1, J1, U2, J2, UN, Jn. But this means exactly that in the partition P, every player Ui prefers a distinct piece Ji. So this is an EntryFree division of the cake into n pieces. Okay, and the theorem that I mentioned here, without a proof, is proved using. So they proved it in a certain way. We will generalize it to the setting of multiple cakes and prove it using some generalization of the KKM theorem. Okay, so here is the generalized setting. So now, instead of one cake, we have multiple cakes, and each one of them is to be partitioned into some number of pieces. So we have a number of parameters here. Number of players will be always n. Number of cakes will be always k. Number of pieces in each cake will, so in this example, I partitioned 2 cakes into 3 pieces each, but in the general case, we can partition each cake to different number of pieces. So the number of pieces in cake 1 will be A1, and number of pieces in cake AK will be AK. And we always assume again that the players are hungry and their preferences are closed. Now we define the notion.
I think you're muted.
Now can you hear me? Good.
Yeah, now we can hear you. I think you were muted for like 5 seconds.
Okay, thank you. So now we define the notion of M EntryFree division. So a partition, so an M EntryFree division is a partition of the K cakes into A1 pieces in the first one, A2 pieces in the second one, and so on, AK pieces in the last one, such that we can find M players that prefer pairwise disjoint K tuple of pieces in this partition. So in this notation, I eliminated the parameters NK and A1 to AK just because I assume we fixed them and we all know that these are the parameters. And now M will be the number that we are investigating. What is the largest number of players that we can guarantee that each one of them can get a disjoint K tuple of pieces from the cakes, okay? So for example, in this partition that we see here, we can see that this is a 2 envy-free division of the two cakes, because players blue and green, we have two players, blue and green, that prefer disjoint pairs of pieces. Okay, so we can assign these pairs of pieces to them without them fighting over a piece. Okay. And we will use this notation along the talk. So we write n a1 to ak curly arrow m if whenever we have n players and k cakes that are partitioned to a1 pieces, a2 pieces, ak pieces each, then there exists an envy-free and an envy-free division of the cakes. So just to practice this notation, here is what Strongquist and Woodell tell us. So the classic envy-free division cake tells us that if we have n players and one cake that is to be partitioned into n pieces, then we can find an n envy-free division. So we can divide the cake into all the players. Okay. Now we want, instead of one cake, to go further into two cakes. So the most desired situation would be that we have two cakes, we have n players, we want to partition each one of them into n pieces and to give each player a pair of pieces, a disjoint pair of pieces, and everyone is happy. But it turns out that this is not always possible. So we can come up with certain preference sets in which the n players, in which there is no such partition of the cake. So we have to do something in order to be able to get n envy-free division. One way would be to enlarge the number of pieces that we allow in each cake. So Coltier, Neyman, and Su showed that if we have two players and two cakes, and instead of dividing each cake into two pieces, we take one of the cakes and divide it into three pieces, then suddenly we can satisfy the two players. But one piece on the second cake will remain uneaten. Okay. Another way to overcome this is to enlarge the number of players. Now, if we divide the cake into two pieces each, then we can find two players that get a two disjoint pair of pieces from both cakes, namely all the cakes are eaten, but one player remains hungry. Okay, but we cannot do both. We cannot have two players and two cakes in it, two pieces in each cake. So these results of Coltier, Neyman, and Su kind of like opened a line of research of trying to see what we can say in general about how big we can make the set of satisfied players and under which conditions. So together with Neyman and Su, we proved that if we have a set of players of size P and we have K cakes that are partitioned into n pieces each, then we can satisfy some portion of the players. So some number P over roughly K squared players can be satisfied. In particular, this generalizes this result that I mentioned here. So if we, instead of taking n player, we take two n players minus one, and we divide each cake into n pieces, then we can satisfy n players. So we can divide the entire cakes between them. But the question is whether this result can be generalized too. So question, is it true that if we take n players and we enlarge the number of pieces in one of them, instead of n to 2n minus 1, can we satisfy all the players? And this is an open question that we don't know how to do in any one of the methods that I will discuss today or in the paper that I'm discussing. What we can prove is that instead of, so remember we want to prove n here. Instead of proving n here, we can prove 2/3 n. And this is what I want to devote the rest of the talk to show you this result. If we have n players, two cakes, one of them is to be divided into n pieces, the other one into 2n minus 1 pieces, then we can satisfy 2/3 of the players. I want to mention that this is not true if we divide the second cake into 2n minus 2. And this is the reason why the conjecture number here is 2n minus 1. Because if we just take one piece out, then we can no longer satisfy all the n players. And this we show too. Okay, so we have a list of results here, and there are more results that you can find in the paper that I'm discussing now. But I will mainly focus on this result here. Now, all the reason that these results are green and these results are magenta is that these are the positive results. So we can show that this implies we can satisfy some number of players. And these are the negative results where we can show an example where this does not happen. All the green results follow from the following theorem. So the theorem, and here is the motivation for discussing fractionally balanced hypergraphs. So the theorem is that if every fractionally balanced hypergraph with vertex sizes n, a1 to ak has a matching of size m, then we can satisfy m player in the corresponding cake division question. Okay, so this does not work in the opposite direction. So there might be cases where we can solve the cake division question, but still it will not be true that every fractionally balanced hypergraph has a matching size of size m. Okay, but to prove cake division results, it is enough to prove results on the matching numbers of fractionally balanced hypergraphs. And this is why we're interested in these. So to prove this theorem is basically a generalization of the Monnier-Sue theorem. So the proof is very similar. We take the set of players of size n. For every partition, we define a k+1 partite hypergraph. So k+1 because we have k+1 sides here. And the hypergraph will be all the k+1 tuples ui, j1 to jk, such that player ui prefer the tuple of pieces j1, j2, jk, given the partition P of the k cakes. And the theorem that we proved using a generalization of the KKM theorem is that there exists a partition P so that the corresponding hypergraph H of P is fractionally balanced. And since we know that, then we know that this H of P is a fractionally balanced hypergraph with vertex sides n to a1 to ak. So by this blue condition of the theorem, it has a matching of size m, and such a matching corresponds to an EntryFree division of the cakes in the partition P, right? There exists some M players preferring disjoint K tuples of pieces, like before. Okay, so this ends the motivation part of this talk. Any questions so far? Okay, so now I want to use the time that I have left to show you how to prove this result, which actually follows from the previous theorem and the theorem that every fractionally balanced three-partite hypergraph with vertex sides n, and 2n minus 1 has a matching of size 2n over 3. Okay, so this is the theorem that I want to prove now. This is a theorem completely on hypergraph, three-partite hypergraph, on matching numbers of such hypergraphs, and it doesn't deal with cakes at all. Okay, and this theorem actually will be proved by a different topological tools, different than the ones that I mentioned so far in this talk. And this will be the topological Hall theorem that is in the title of this talk. So given a graph G, the matching complex M of G is a simplicial complex with vertices being the edges of the graph, and the simplices are the matchings in the graph. So clearly this is a simplicial complex because it is closed down. So now suppose we have a three-partite hypergraph on vertex set V, U, and W. And now for every set K that is subset of the first vertex side V, we define the bipartite graph G of K on the sides U union W with edge set EK, where EK are all the pairs UW, all the edges UW, such that together with V, they form an edge in H for some V in K. So we take all the vertices in K, we look at all the pairs that together with some vertex in K form an edge in H, and this will be our bipartite graph G of K. Okay. And now, what a very special case of the topological Hall theorem of Aharoni and Axel from 2000 tells us, that if for every such K we have that the topological connectivity eta of the matching complex of this G of K, this bipartite graph G of K, is more than 2/3 the size of K, then the matching number of the entire three-partite hypergraph H is at least 2/3 the size of V. Okay, so I threw at you some very advanced notions that I haven't defined, and in particular this topological connectivity eta, which is defined here in small letters, but I don't want to get into this definition, because what we will actually use is some combinatorial parameter that will replace this topological parameter eta. So I will not define this eta, and instead I will define some other parameter that we will use in the proof. So let's do that. So now, first, instead of discussing, can you still see my slides? Because okay, now it's okay. So instead of discussing matching complexes, we can go to the line graph and discuss independence complexes. This should be independence and not independent. Independence complexes of the line graph, right? So now our vertices will be, our vertices of the complex will be the vertices of the graph, and the simplices are the independent sets of the graph, right? And clearly this is a simplicial complex because it is closed down. And now a theorem of Meshulam tells us that if we have for every, so the theorem tells us as following. So for every edge E of the line graph L, or of any graph L, the connectivity of the independent complex of L is greater than the minimum between the connectivity of the independent complex of the graph that is that we get by removing E, and the connectivity of the graph that we get by exploding E. This is exploding E plus 1. I will explain this, and I will explain this in terms of a game that we call the Meshulam game. So the Meshulam game goes as follows. There are two players, con and non, and we have our graph L. Now at each step, con chooses an edge in the graph L and offers it to non. Now non can do one of two things. It can either delete the edge E from the graph, or it can explode E. What does that mean? It can remove the two vertices of E and all their neighbors. Now, the result, psi, of the game is defined as follows. If by playing this game at some point remains an isolated vertex, then psi is defined to be infinity. Otherwise, psi is going to be the number of explosions until the graph disappears. Okay, and what this theorem of Meshulam actually tells us is that eta of the independence complex is greater than psi of the independence complex. So now, instead of discussing the connectivity, we can discuss the combinatorial property of playing with two players and edges in a graph and exploding, deleting, and see what we get, right? Which is a completely combinatorial thing. Okay, so here is a translation of the game into the matching complexes, because this was in terms of the independence complex. So con chooses an edge, meaning he chooses two edges in the primal graph that are connected by a vertex. This is an edge in the line graph, right? And he can either delete E, meaning make these two edges separate. So now they are topologically a matching, although they have the same vertex U. Or he can remove U, W1 and W2 from the graph. This will correspond to exploding. Okay, so this is just a translation. Another theorem of Aharoni and Axel that I'm going to use is that if we need at least T edges to dominate a matching F in G, then the topological connectivity is at least this T. So here is an example. Suppose G is bipartite and F is the following set of edges. So this is a matching. It is topologically a matching. These were somehow disconnected in the Meshulam game, but now they are a matching. So since G is bipartite, we need at least two edges in G to dominate F, right? Because every edge here can touch or can intersect at most three edges. It can intersect two edges here by the vertex U and one edge here in the vertex say W3. And similarly here. So to dominate these 4 edges, we need 2 edges of G. And therefore, eta of the matching complex by this theorem is at least 2. Okay, so this is just a theorem that I'm going to use without further explanations. Okay, now we are ready for the proof. Okay, so we want to prove that every fractionally tripartite hypergraph with vertex sides of size n and 2n minus 1 has a matching of size 2n over 3. And our proof strategy will be as follows. We take a fractionally balanced hypergraph, tripartite hypergraph with sides n and 2n minus 1. We want to show a large matching. We will play the Meshulam game to show that for every such k, psi of the matching complex of G of k is at least 2k over 3. And this will be true for every k. And then we will apply the topological Hall theorem to get that this means that the matching number of the entire hypergraph H is 2/3 the size of V, which is n. Okay? Okay, so let's see how we do that. So we have 2 lemmas that we use. The first lemma is that if we have a bipartite graph G on vertex size U and W, and if we have in G a set of edges F that contains only either K11, namely disjoint edges, or K12, so stars with 1 vertex in U and 2 vertices in W, and these are disjoints. Then psi, the result of the matching complex, the result of the Meshulam game on the matching complex of G is at least the size of F over 3. So let's play the Meshulam game to show this. Okay, so we play the Meshulam game as follows. So con offers none all the K12s. And remember, these are edges in the matching complex, right? So con offers none all these edges 1 by 1. Case 1 is that none explodes one of them at some point, right? Then we gained 1 in psi from the explosion, and we lost 2 edges because the explosion just removed these 2 edges from F and no other edge in F, right? So by induction, we have that eta is at least, or psi should be here, at least F minus 2 over 3, this is the induction hypothesis, plus 1 from the explosion, which is greater than F over 3. Okay, so this is case 1 where none decides to explode in some point. So the other case is that none does not explode and just disconnect, namely delete the edges for all the K12s. So then we are left with a set of topologically disconnected edges F. So this is a matching now topologically. And as we saw before, it needs at least 1/3 of the size of F edges to dominate, because an edge E can dominate at most 3 edges in F. So by the other Aharoni axial theorem, we have that in this case, eta is at least F over 3, and we are done. Okay, so this is the part of the proof where we use the Meshulam game. Now, in the other lemma is the first place where we use the fact that the graph is fractionally balanced. So the lemma is that for every such G of k, remember from the Aharoni axial theorem, for any such bipartite G of k, we have a set F like we need of size 2k, which will give us the 2k over 3 that we need in the theorem. And this follows from the fact that the hypergraph is fractionally balanced. So since H is fractionally balanced, there exists a fractional function. This is just the function, the fractionally balanced, the fractional matching that is balanced, reduced to the two sides UW, satisfying that the degree on every vertex U in U is less than 2, the degree of every vertex W in W is less than 1, and the degree on the entire set in U is more than 2K. To see this, just work with the sizes of U and W and with the conditions of what it means to be fractionally balanced. This is very easy to see that such a function exists. But now we use the fact that GK is bipartite. And since it is bipartite and there is such a fractional function, there is also an integral function that satisfies the same thing. And such an integral function gives a set F like that, where F is exactly the edges that is mapped to 1 by F prime, by this integral function. And together, these two lemmas and the topological Hall theorem gives us what we need. So this is the end of my talk. I'm leaving you, there are many, many open questions in this area. Like there are more open questions than closed questions in this area, but I'm leaving you with the one question that I don't know how to even start to approach, because it seems that all the topological tools that I introduced do not fit into solving this problem. And the question is it true that if you have n players, two cakes, one is to partition into n pieces, the other one into 2n minus 1 pieces, then you can satisfy, using some partition, all the players. Thank you.
Let's thank Shira for a wonderful talk. Any questions? You can just unmute yourself and ask.
Let me stop sharing, maybe. Okay.
So any questions? Can you show us maybe some other open problems since you already started?
Yeah, so we have a lot of parameters that we don't know how to approach. So it's kind of hard to describe a list of open questions, because all of them will look the same, like of the same format. So so now go up, instead of 2 cakes, into 3 cakes. I don't know almost anything about that. So there are some trivial bounds that come from very well-known theorem in matching theory, so Faraday theory and such theories that are very well known. But these are just the trivial bounds, and it is clear that better bounds can be achieved, but nothing is known in 3 cakes, for example, and not much was investigated. So it's hard to kind of like list a list of open questions, but I think that maybe in our paper there is some open questions that we can offer if someone is interested in looking.
Thank you. Is your paper on the archive?
Yeah, it is. There are also like open question in the negative side. So can you find examples where the preferences that does not, some preference sets do not admit a proper fair division into some number of players. So and again, these are questions in terms of cakes. You can ask questions solely on fractionally balanced hypergraphs. I think this is a very interesting family of hypergraphs because it arises every time you have kind of like a Sperner type result or a Brouwer fixed point result on like a topological result of this nature, then somewhere in between lies a fractionally balanced hypergraph. So it's an interesting family of hypergraphs that needs a lot of investigating yet.
Thank you. Any more questions?
So the topological Hall theorem that you use, is that something that only applies like to 2 cakes? Is that why we can't get anything for 3 cakes or higher?
No. It applies for it. The theorem that I stated is a very, very special case of the Hall theorem. So the Hall theorem discusses ISR, which is independent sets of representatives. So you have a set, you have a simplicial complex that is defined on a family of sets, and it gives you a condition to the existence of a set of representative, one from each set, that belongs to the complex. And it is a very, very wide setting that you can use in many cases, not only for hypergraphs, and in this case, it can be used for more than 3 cases. The obstacle is in the matching theory. So we can prove things, and in the Meshulam game. We know kind of like how to play the Meshulam games in 2 cakes. We know many things about matching theory in bipartite graphs and in graphs in general. And we know less on these things for 3-partite and more and larger hypergraphs. So the obstacle lies there, but the Aharoni axle works in general, and also not only for 2/3. It works for any constant C that you. So replace the 2/3 there with any constant C, and it's still true.
Any more questions? Okay, in that case, let's thank Shira.
I see things in the chat.
Well, so, okay, so I should read the last one. The last one was from Sarah. She said, thanks, Shira, for a nice talk. The first 2 were from pre-talk.
I see. So thank you so much. It was a pleasure speaking.
And then Amze also said, thanks, I have to run.
Okay.
Need to run.
Thank you.
Yes, very nice talk. Thank you.
Thank you so much.
Thank you.